Start with the regular presentation. Okay, so welcome everyone to another CPTAP session, call number 103. And today's talk is the topic is synchronization use cases and requirements for data center networks. So our speaker is Liuyan Han. Liuyan Han received her PhD degree from Tsinghua University in 2009. She's working at the China Mobile Research Institute and currently director of the Transport Network Center, with her research focused on time and frequency synchronization, transport network solution, and she has been actively involved in developing the CMCC's time synchronization strategy. So I think with no further ado, we give you the floor.
Okay. Okay. First of all, I thank Amanda for inviting me to give a presentation at OCP, and I would also to thank you for adjusting the meeting time due to the time difference in China. Today, I would like to present some considerations on synchronization use cases and the requirements for data center network, and I also give a similar presentation in HBOE 1588. For China Mobile, we have built a national P2P time synchronization network for the mobile communication systems. But the use case of P2P in the data center field in China Mobile is still very limited, and we just began to study this point, and we hope to expand the P2P application in this area in the future. This slides first. I will give some background of the data center and then to discuss the requirements and use cases of time synchronization in data center area, and last is a conclusion. First, development trend of communication network is shown in this slide. For the China Mobile, we are developing rapidly in the computing network in recent years, and now the network includes 4 regions and some central nodes and some provision nodes and more than 1,500 agent nodes now. The optical transmission network between the data center is up to 400 gigabits, and the total computing capacity is more than 10 EFLOPS. There are 2 trends with the rapid growth of computing compatibility demand. One is the distribution from intra to inter building. Since the growth of computing capacity demand growth is very rapidly, about 750 times in 2 years. So the scale of distributed computing is expanding. Maybe some single data center computing capacity is limited by site area or the power supply. And in the future, distribution computing will become from intra-building to inter-building. The second trend is data center services are evolving from general purpose computing to AI computing. And the ratio of AI computing and general purpose computing may be about 33 in 2030. The AI computing will grow 500 times in 10 years. So the DCN and the DCI technical trends is also very hot in the research area. For the DCN, for AI, focus on ensure no congestion and reducing transmission delay. The key area is RDMA. For the RDMA purpose, the requirements include low latency, large bandwidth capacity, high reliability, and so on. The challenge is a typical TCP and IP protocol is too inefficient for this area, for this use case. So the technical roles include some different roles, IBROC and IRAP. They all plan to give a more efficient forwarding in the data center. For the DCI, the technical trend focus on low cost and large capacity to use a larger interface, bandwidth interface, from 200 even to beyond 1T. And other requirements include to reduce the electrical switch, to use optical switch to reduce the latency, and also to use a flexible bandwidth extension suitable for DC use case. So we can see that the data center is developing rapidly, and its technical is also very changed fast. But we can see if the time synchronization can bring some very important value to data centers. Currently, the data center mainly rely on the NTP to give some time information, where PTP in the data center is very limited. Maybe some scenarios PTP has been used partly for the in-band OM, the latency, and packet loss measurement. This time step is basic information, so we believe that time synchronization may contribute to enhance some performance at service and network levels, and here give some use cases in the service level and network level. The first use case is about distributed computing. The high precision time synchronization between computing nodes may enhance the training efficiency of AI models. The HPC, the hundreds of computing nodes work together to complete the whole computing task. So its operation involves sending and receiving the data between all nodes. During this operation, a computing node can only start the next computing task once it has received the data from all other nodes. Therefore, the efficiency of network communication and the computing task planning become very important. Currently, the planning of computing tasks is mainly based on estimated average distributing across various computing nodes without considering the time taken for the data transmission. If there is a high precision time synchronization among all the nodes, maybe we can accurately and centrally to plan the training tasks to reduce the network congestion and significantly improve the training efficiency. In this use case, we also to analyze some basic requirements for the SIG network. In this use case, the application end is a computing nodes, the CPU nodes, and the time accuracy only to require the relative time time accuracy between the nodes. The number of the hops, if we consider the inter-building connection, maybe it's up to 6. If we only to consider a single DC, maybe it's up to 3 to use a spy-leaf architecture. The second use case is about distributed databases. The databases, it may use a commit with the distributed transaction protocol. Under this protocol, whenever a database transaction commits, the database is locked to prevent subsequent transaction from access the old data. So there is a 2 times epsilon time delay guard before the next transaction can be committed. So if we enhance the epsilon, the time accuracy, the higher the read and the write frequency becomes, and the larger the database throughput is. So we can use a higher time accuracy to enhance the database throughput. In this use case, the application end for the synchronization network is a database in inter-DC or intra-DC. So for each DC, it may need the epsilon time. And intra one DC, the relative time accuracy is efficient. It also it's better to have the time holdover performance for each DC. And there is no requirement for the time synchronization between the switches in the network. The third use case is related to data forwarding at the network level. We think maybe we can combine a global controller with a high precision time synchronization and the data transmission. So if the data transmission is based on time windows, it may improve the forwarding efficiency and reduce latency. Currently, the transmission protocols inside the DC operate on the best effort basis, which make it difficult to totally avoid data concurrency in advance. They can only adjust or control the flow when congestion is happening or about to happen. So we think maybe we can to introduce the time synchronization in the data forwarding protocol. It may greatly enhance the forwarding efficiency and reduce latency. This architecture allows us to control the data sending time of the switching and the servers to ensure the deterministic forwarding behaviors inside the network. In this use case, the application end for the time synchronization network is switchings and computing network. So it also requires the switchings in the network to obtain the time information. Maybe the switchings need to support boundary clock or to support TC plus OC, this clock type. The last use case is time synchronization for delay management. The high precision time synchronization provides accurate one-way delay measurement ability for computation tasks and enabled forwarding parse planning based on precise delay information. So we can use a high precision time synchronization to conduct a precise one-way delay measurement, allow us to build an accurate delay map for all the network, especially for the DCI, which is sensitive to the latency. So we can use this information to employ minimum delay stringency to select the parse for the data forwarding to enhance the computing efficiency. So this approach not only optimizes the overall performance of the network, but also ensures that the data reaches its parses with a minimum delay. So we can maybe expand the PTP protocol to measure the one-way delay for each section in this network. In this use case, the application for the network is also include all the switches and the computing network. So the switches also need to support boundary clock or TC plus OC to obtain the time synchronization information for the next delay management. So based on the mentioned changes in the data center use case, we summarize that the time synchronization in the data center network requires limited hops, maybe up to 6 hops, and with limited distance, maybe within 10 kilometers if we don't consider the long distance DCI interconnection, only to consider the distances inside the DC. And the amount of application client is very large compared with a backhaul network. It may be more than 10,000, and the relative fixed topology structure. For the data center synchronization, one issue we think maybe how to obtain the time source. One method is to set a time source with a GNSS receiver within the DC. So time error of DC is come from the GNSS receiver. But one problem is the GNSS signal lost. The sync between DCs will be lost. The other method to obtain the time source from the telecom network, for example, from the metro network, the PRTC or ePRTC, it can reuse the existing time source network devices. For this application, the time error to the TC will include the PTP time error in the network. And if we request the PTP protocol inside the DC is different from the traditional 1580H, it may request the PTP protocol conversion between telecom and DC network. Another issue is the time path arrangement. The DC network requires higher reliability and shorter switching time for the time path rearrangement compared with the current PTP network. Maybe two directions can be considered. We can use a faster BMC or to use a deterministic time path with a backup path to be planned before the network used. So that's all the presentation. In conclusion, we think the DC time synchronization is different from the mobile backhaul network with simpler but higher scalable topology and huge of clients. So it needs new PTP protocol for data center network synchronization. Next, we will further study the combination of time synchronization and DC services, such as to research study the time-based traffic forwarding mechanism and delay management. So that's all. Thank you.
Thank you very much. Okay, let's open the floor for questions. Any questions from the audience?
Good afternoon, or good morning, Ahmad.
Morning.
Yeah,
go ahead.
A question that I have is, what is the plans to use a telecom profile on this environment, this data center environment, or is planned to use different profiles?
I think maybe the the number of clients is too huge for the current PTP protocol. Since for the metro network, we use in China Mobile, we use a boundary clock architecture. So for the boundary, it uses multicast and for the boundary clock, we must to put the switches in the DC network to support time synchronization. If we use a boundary clock architecture, the client number is not an issue. But we use a TC or other method, maybe the client is too huge and it may be expanding in the future. The DC, the GPU number is expanded, for example, from 10,000 to the 100,000. Then the client number will be extending at the same time. It may bring some issue to the current PTP TC protocol.
Okay, it's not clear for me, but in my opinion, I'm from the telecom side, but I'm just to say that I'm not arguing that telecom profile is a must for data center. No, it's a doubt that I have. What I think is important and relevant is to have some consistencies and something that is interoperable and widely available. Telecom profile, at least in service providers, it takes several years to get adopted due to hardware constraints. So Ahmad might have a different position because Meta has done differently, no telecom profile as far as I understand, and that's why now I just came out from another webinar related with this topic, and suddenly I start to listen the telecom profiles. G8275.1 is targeted. Was a surprise for me, but I'm not against it. That's why it's my doubt and try to understand what we need to consider and what is the trend in the industry to achieve timing synchronization in data center environment. That's my doubt.
Okay. Just to elaborate on that, like we came up with this like simple PTP, basically to get rid of a lot of the handshaking, and we use unicast strictly in our infrastructure, and that's perhaps because of the scale and how we basically do our routing and everything, and we strictly use transparent clocks, so no boundary clocks. But again, I am like aware that we're not like the only operator in this field, and not everyone is like the same, but that has been our approach, and we've been 100% open source everything. Like even our protocol is open source available. We call it as a DC profile.
Okay, Ahmad, thank you.
I have a question, Ahmed.
Go ahead, Hisham. Go ahead, Hisham.
Yeah, so what is the best architecture for AI clusters in a data center? There is the spinal leaf, there is Dragonfly Plus, Cerberus, which was presented in SECOM a couple of years ago. So what do you recommend as the best architecture or the topology architecture for AI clusters in a data center?
Oh, the architecture topology in the data center maybe it's not related to the time simulation, but I think the main topology is still use a spy leaf, not the dragonfly. For the spy leaf, it can achieve the full mesh connection between any nodes with a minimum hops. So for the AI, it's important for the AI training services. If we use other topology, it may be for some traffic flow, it will need more than one hop to its destination nodes.
Maybe we can go to slide number 7 and have you elaborate more on that, like because that is something we're very interested in general about.
You mean
because
7
again, that
or
7,
which slide? 7.
the case scenario 1, yes, this one,
Oh, thank you.
where like, for example, this is something I mean, I think everyone has been wondering about. Do you mind if we elaborate more on this? Like, we want to see what are your thoughts? Like, there are certain things we've been thinking, like, yes, like time-aware collective scheduling. So, and you have like all those things, like the basic data sent and received without timing versus like if you can plan ahead and all of these things. And you mentioned here, you're suggesting a centralized scheduler. It's great if we can elaborate more also like with the community here. Let's see what are the things that are already established, what are the things that we still need, like for example, if we are trending toward a direction, what else, let's say, we can get from the provider to add to make, like, things even better. So do you mind we start with this, digging a little bit on this?
Oh, to be honest, we just give some concept or some maybe potential direction. Since for
No,
the China
I'm well
Mobile,
aware. It's a concept,
yeah,
sure.
yeah,
But
yeah,
let's drill
yeah, yeah.
down a little bit more on the
I just
ideas.
looking
I will
from
help.
my
I will help as
research.
well.
This is why for the China Mobile, we didn't have very much
Clusters.
impact on the GPU
Mhm.
vendors. This we just to use the services. If we want to support this use case, maybe we have to change some AI model training the schedule mechanism. For the current spy leaf inside one DC, we think the transmission delay is symmetric. For any flow, we think the delay is the same. It's a condition for the AI training. We think the transmission delay is the same. But if we maybe we go back to the trend. If we in the future the distribution is from inter to the inter building, then the transmission delay maybe it become not so symmetric. For some flow, the transmission is from the one side to other side is longer than other transmission. In this condition, maybe we have to consider transmission delay in the AI training task assignment. Then we can get the best result, maybe.
So let's say when I mean this is just a consideration. Let's say if the GPU is also time aware, where you can measure now the duration for
Yeah.
the compute of whatever you have, like an epoch or whatever, would that help in this model, in this idea, in this configuration?
It's just the idea. We maybe we plan to give some.
I know in the idea. I'm again. I want.
Yeah,
I want
but
to.
up to now there is no
brain,
test.
basically.
There is no test up to now. Yeah.
So I can share like what we have done so far is basically we thought like if we can measure precisely when the GPU is basically performing something. Of course, that needs some changes also in the GPU. Let's say with PTM, you get like the precise time. PTP gives you the precise time to the node, and then from the node with PTM, you go to CPU. From CPU, come back to GPU. So then the GPU can do two things. One, it does the reactive thing, meaning like you do timestamp, or like let's say you precisely can measure durations for certain compute. And the other one is you can actually wait until a certain time before you start executing things. That's unfortunately how it is in the world we live in, where causality is something you cannot break. So any scheduling in a causal form is with delays that you can always delay things. You cannot put things ahead. If you do that, I mean, of course, it's in a periodic system, you can always put things before, but if you start from a cause and effect, everything is based on delays. So that portion is taken care of, and you get to the point where you have, let's say, y1, y2, and until yn, where you want to now basically handle things on the network. For that one, we thought also about some other things where the NIC can give you basically a precise time when a packet departed. That's the reactive thing. And the active one is the NIC will hold on a packet before it transmits the packet at a specific time. So
Yes.
that one is like basically scheduling, or like if you do that with a frequency, then you have pacing. So all of these are available, but I still don't have this algorithm. Like, where am I going to benefit the most? The only thing so far, basically the thesis so far is if you look at these all-to-all deep, like basically these fabrics where you have disaggregated fabrics, basically, where you have uh, like the need for, like, you basically don't have any time awareness, and everyone is transmitting, just for lack of words, transmitting irresponsibly. Every node just throws everything in the network and says, network, deal with it. And you don't want to have congestion. I mean, you have congestion. You don't want to have losing packets. What you do is you go for deeper buffers. The problem here is, again, aside from cost and all these technical things, buffers tax you twice. You basically have to wait for writing and you have to wait for reading. Opposed to this, if you were able to somehow optimize things on the exit from the network egress, you can have a, like, basically the buffers are basically living by the transmission. So you transmit based on a schedule, and on the receive, you have like maximum throughput on the receive on every node that things have to go. And of course, it's a full duplex, let's say. It is a full duplex. And it's a Ethernet, right? So then you will have everything transmitted like in a way that you really are next to not using the buffers. So that basically gives you the benefit of like saving that time for reading and writing the buffers. But to do that, we thought like, okay, that needs to be a centralized controller. How you can have that in, I mean, if you don't, then you have to account for the time and the latency that it takes for the commands to go to all the nodes from a central node, which that might eat from that saving that you were banking on for the buffering. And that centralized to a decentralized thing is a magic, because you have to basically come up with something as decentralized but emerges in a behavior that you were expecting from a centralized node. And this is where we are stuck.
Yeah, I think you said some important things. Because in current network, in the data center, the distance is very short. And I also think the path is symmetric. All the paths is almost the same. So we can think the transmission delay, we can ignore the impact of the transmission delay. And we can use a minimum buffer to reduce the latency caused by the buffer. But if the DC site is larger and maybe we cross the building or even cross the region, then the transmission delay, we can't ignore its impact. Then we must to use some larger buffer to solve this problem. And maybe we need some we want to know the transmission delay and to do some control on it.
Ahmed, if you remember, MIT folks, they did something similar to what you are talking about, called, I put it in the chat, called FAS, where you have a centralized arbiter or controller, which coordinate who can transmit and when. And by doing this, you have zero queuing. So your idea really have been investigated by MIT, and you can look at what I put in the
Yes, for
chat.
sure. I will look at it. That's very nice that you have a reference.
Yeah, they have simulation results. They have everything. Not everybody liked it, and the people in MIT don't have commercial deployment for this idea, but I think it describes what you're talking about. It's a smart idea, but
and it's very interesting. Like even source code is available. Everything. Wow.
Yeah, look at yeah, exactly. You may talk to
fastpath.mit.edu.
Yeah,
for everyone else.
and if you are interested, Hari Balakrishnan, the main professor for this, is really a good friend of mine. If you want to talk to him, I can.
Yes, please. Yes, please.
Yeah.
So, yeah. Anyone else in the audience about this? Sorry. Go ahead. Yeah.
Amanda, I also have a question. Since we think we have a long, you have a long experience to study the time synchronization in the data center. So what do you think the main use case or main scenario to introduce a precise time synchronization in the data center?
So yeah, the best thing so far we have is basically what you have in page 8, the next one. Where is like the next page, if you go to your slides, is basically the distributed databases so far. And there is
database. Okay.
Sorry, your use case number 2, yeah, where you have commit and wait, and the wait comes basically from the worst case scenario for the clock skewness. And traditionally, this was justified when you had the latency was, big, and then the clock skewness, again, delivered by NTP was like somewhere, again, with a round trip, with like, I don't know, some margins of safety was like 20 millisecond. So
yeah,
that's like making the switch from NTP to PTP to be like orders of magnitude, like much better, let's say in terms of clock skewness, would basically put you in a point where the clock skewness is, again, orders of magnitude less than the smallest latency, technically giving you a commit zero wait like architecture, which when we did that in practice, we couldn't get commit zero wait. It became commit less wait. And that is because the skewness started like coming from other things, because again, things were processed in layer 1, sorry, in layer 7 rather than layer 1. And then I started like, again, thinking about like, okay, let's dig into this totem pole of OSI model and see where are what's the source, what's the biggest source, what's the biggest contributors. And I figured out that maybe we should go with these concepts of smart NIC and do things at layer 4 or something, and have like the NIC not just do like sending packets back and forth, that the NIC be a little bit smarter. And that is where Kevin Stanton shows up and tells me, hey, I have something that might be interesting. You can basically have, even though things are like, are going to the OSI model, but you can have the CPU with the clock skewness also back to tens of nanoseconds. And that is, the solution is PTM. And I basically just dumped everything I was doing on that idea of like quote unquote smart NIC, because smart NIC has been abused. Like if you just put a processor on a NIC, they call it like I don't believe in that. Smart NIC, I think it's a concept we have to wait for it until we get it. Where like you tell the NIC, hey, there is this, let's say, I don't know, scheme you have to do where like, and then NIC takes care of all the scheme, like all kinds of things, like distribution, broadcasting, atomic operation, dirty write, like all of these things. And I know I might get like some colleagues getting back to me or some vendors like, oh, we already have it. I know, but I don't have an application for it. So hold on that one, right? So basically with PTM, it looks like I have all the freedom to do things now in the NIC, but then that's where I came across Edward Lee's interesting CAL theory, which basically says anywhere you go less than the latency, it's diminishing returns. So you're not going to benefit that much. But I mean, still going down to the level of latency, still there are things we have to go through, like the disk operation. All of these things are still things I cannot control, but I can measure them. That's at least what is good here. So
yes.
we are like, let's say, asymptotically reaching commit zero wait.
Yes, so they can say that NTP is not enough and use a precise time synchronization.
Yes.
You can enhance the performance. Okay.
And like more importantly, with regards to NTP, again, NTP, very thankful to NTP. NTP is always there, and we use it. Actually, there is this clock fusion method that I spoke about. I introduced it, where we use basically PTP, multi-sources of PTP and NTP, and then we are always watching like the servo basically is a distributed thing. The servo watches like the client basically watches multiple clocks and NTP, and then tries to give you basically the best one it chooses. If all of them are good, it just takes basically the lower number, and you use basically that one. Uh, the biggest problem with NTP is the statistics that you cannot really rely on, because I mean, you can always have statistics, right? But the statistics has like you have a harder time with like the stationarity of it. And it takes longer than, let's say, PTP, if you have this multi-sources, to find out that, hey, now you are operating bad. So usually takes much longer in NTP to find out that, hey, you're doing something wrong, because all like I can describe that all in some drawing.
Mm. Mm.
And is this also something hypothetical like this on the case two, or do you guys have already something for it? Liuyan, do you guys have already some implementation on this, or is also hypothetical?
We plan to do some experimentation this year, but I haven't. If I have some progress, I can discuss with you.
Wonderful. And so
Yeah.
use case number 3. So how is that differing from these other things, like the forwarding? Is this also going through a network? Like, what is it basically just to have, let's say, a time-aware Rocky? Is that something like this? Like what?
Yes, something like that. If we
Okay.
use the wrong key, then the time over wrong key. If we use some other protocols, maybe to introduce the time to the protocol.
Mhm. So going back to the audience, any comments anyone wants to add?
Yeah, can we
Oh, great.
say, Ahmed, that NTP is more efficient than BTB, but BTB is more accurate?
How I look at like, I mean, it's just my point of view. I always look at it like gross and fine. So the good thing about NTP is you're not gonna get fooled by, let's say, a faulty transparent clock, or let's say, I don't know, in case of, let's say, you're stuck. I mean, with PTP, you're stuck with your local network usually. And even let's say in 10 years, 20 years, let's say all these things we've been talking about really takes place, and you have every switch in the world like turned at least to a transparent clock, you still have a lot of hops to go through, right? So you with NTP, you're not relying, you basically don't have those, let's say, measures, but of course, with a huge cost, like you have all the jitter and everything and so on. So basically, all I'm trying to say, the essence is it's fine to be wrong if you know you're wrong, but it's not fine if you're wrong and you don't know. And that's the problem, let's say, if you want to completely rely on PTP, right? So PTP, of course, will provide you the precision at the end when you want, but then it's good to have like, again, as a control engineer, I always like to have cross validation, right? And then cross validation is very challenging when you have a single thing. So what I do is like I go for a trending of that single thing, and then I use that as, again, this is Kalman filtering, right? So then I use the trending as my model, and then I look for observation, and I try to see, are they matching or not? And then based on that, and again, you can use covariance and eigenvalues, whatever, you can figure out like a like a weighted sum, a weighted average of the two. Which one should I rely more, observation or model? And then you go between the two. So I don't have that one yet, let's say, for NTP and PTP. What I do is basically I take the PTP like multi-sources and I take a covariance. I try to look for no relation between the two, but the means have to be at least within the standard deviation of each other. Otherwise, I weed them out and I pick one. And so NTP is basically just, hey, everything as long as under NTP. So it means like we never give, with PTP, we never give anything worse than NTP. So that's the idea. But again, there is some stationarity of the NTP. NTP, otherwise you're just getting a value. What do you want to do with the value? Well, you look with the value around it. to like, standard deviations. I mean, this just keeps going on, and nothing is written on stone. You come up with some ideas and then you try and see if they work. I mean, the whole thing is just what do you call synthetic? The whole concept of time and chasing time is really just a synthetic thing. It's just a measure of the growth of entropy. Let's be honest.
Yeah. My last question to Lillian is: do you have a publication, a paper about that mesh topology you're talking about? Because and shows that it is better than all these other topology architectures that are known, like that I mentioned to you.
You mean the topology? Or
You said mesh is the best. Do you have a paper or you know about a paper, a publication to show using empirical analysis or simulation that mesh is the best?
I think maybe there is some publication to compare the topology, but I don't have now. I don't have the very solid white paper. Maybe I can try to find some paper to compare the topology.
Yeah, if you find it, because I don't know why you are recommending mesh. There must be some analysis to back up your.
Yes, I think some papers they proposed some other topologies to beside the spy leaf, some other topologies, but I don't know if there is a very uh, uh, very clear comparison between some topologies. I will try to find if there is some paper I can send in. I don't know your address. Maybe I can send it to Amanda
Yes, yes. Send it to
if I
me. Send it to me. I will forward
Yeah,
to her. Sure.
yeah,
yeah.
send it to Ahmed, yes, exactly. Because uh, I think Dragonfly Plus is gaining momentum now, although vendors like Broadcom, when they say,
Yeah, Dragonfly is also
Yeah,
yeah.
like Jericho and all this
Mm,
VOQ and
yeah,
everything. Yeah. Yeah.
yeah.
Again,
yeah,
it's all about like basically figuring out the cues, how to go about the cues and not have like once getting everyone stuck and things like that.
you're
With
right, you're
yeah.
right. So anyway, I'm just curious to find out why you choose Mesh, where many people choose something else. And I would refer you to a paper about Cerberus
Mm.
architecture, which was presented in SECOM. I think I will send it to the group, and you can or, and Ahmed can forward it to you.
Yes, yes, for sure.
Okay.
So let's go quickly to use case number 4 as well. So which you're mentioning like the one-way latency basically is helpful. So is this also basically an indicator for the congestion? You're getting an indicator to have like different routing. Is it something like that?
Um, maybe we can use delay information for several purposes, but this use case is only to obtain the delay information. We can use the information for some strategy or some other purpose. That's the next step.
I see. I see.
Yeah. Mhm.
No, I really appreciate it, since uh, I've been spending so much time on like figuring out applications for all this thing. As I said, like for the first I've been dealing with this whole thing like for about 7 years now. First 3 4 years was like how can I deploy these things and what is needed, basically the how. But then this like last 2 3 years been like why, and I've been like now thinking a lot
But
about all the theories and so on.
yeah, for the use case 4, I think it's not only uh, uh, used in the data center. Maybe we can use it for all the fiber-based networks.
Yes, yes.
Since for now we can't get the accurate fiber data for the network. For the metro network, for the backbone network, we don't know the accurate fiber length and fiber delay. If we can use a time-based information to get the information, to get the delay for all the network topology is very important. We can use this information for some other further extension to do something. Yeah.
Wonderful. Juan, do you wanna speak and like describe like what was your comment?
Hello,
Yes, we can
you
hear you.
listen me?
Yes, yes, yes.
Yeah. Okay, my English is not so good, but
Your English
I
is
try
great.
to
Let's go
uh,
forward.
Thank you. Look, in the real test, I checked the transparent clock solution,
Mhm.
but in my opinion, it's not a good solution because the packet variation
Mhm.
is modified for the traffic, and the time error testing in normal situation was very good, but what include traffic generator, the real mediation left the 1 microsecond
Mhm.
increase a lot, 6, 60, 70, etc. But for me, is a recommendation no use transparent clock in the real scenario. Y es necesario first test the solution. And second is include the position navigation and timing for protect the solution for the attack, for
Yes.
the jamming and spoofing. These are my two comments. Okay?
Yes. So like with regards to transparent clock will definitely take care of like the packet delay when you have basically the residence time. And from our testing with the like the Tomahawk series, we can hit like an error under traffic even for something less than 1.5 nanosecond per hop on a transparent clock. So there must be something wrong, I would say, with that transparent clock, perhaps not doing the residence time properly. Otherwise, transparent clock's job is to measure precisely like the residence time and add it in the correction field. So the only caveat I will say here is if you have a ppm uh, drift or something in the local oscillator of the transparent clock, you have no way to find out about it. And because there is no, like, let's say, servo syncing with the grandmaster to basically figure out like how off you are. Which again, for that, we're thinking maybe we should have like a hybrid of the two, like not necessarily hybrid of boundary clock and transparent clock, and just a client. So there's one client on the switch that is basically just synchronizes with the grandmaster to make sure the time that is used to calculate the residence time is also synchronized. That's all. So anyone else? By the way, Bijan, like, are you here? If you want me to give you some time to describe your thing? I mean, after we finish this.
Yeah, I probably don't have time. Can't fit it in, but I thank you. I'm sorry. Today
No
was a
problem.
pretty odd schedule for me.
No problem. So we can do that for another time. All right. Anyone else? Any more questions, comments? All right. Hearing none. Again, we want to thank the speaker again, Liuyan, and great presentation. Definitely a lot of like thoughts and thought-provoking and all the stuff. And next call will basically have, let me look at the schedule, in 2 weeks. I think it's by our friends in Epson. And let me quickly tell you the title. Which again, it will be in the normal time in 11. I will be in Australia, but I'll still try to make it. Which will be like the latest trends in crystals and oscillators by Madura Fontaine. And if there's no more comments or anything, we'll adjourn for today. And again, see you guys in 2 weeks. All right. Bye, everyone.
Great meeting. Thank you.
Bye-bye.
Thank you. Bye-bye.
Bye-bye.
Bye.
Thank you.
Bye. Have a nice day.
Bye. Thank you.